Hello, this is Carl Perez with Online Class 2 and Math 125 Statistics, Fall of 2012. Uh, 1 minute before we go on to the material in earnest, I want to remind us all there is a complete solutions manual available to you, posted under the Lessons tab. Hello? Yes. Lessons tab in Angel. And I believe the name of the folder is or something similar to 11th edition solutions. Now it's broken down by chapter, and every chapter is a PDF file that contains, again, complete solutions of all problems and exercises included in the text. So if you're wondering about solutions for any particular problem, this would be an excellent and probably the premier resource to consult first, and is available to you, again, posted totally and in completion under the Lessons tab in Angel. Okay? So look for that if you're looking for particular solutions for any particular problem. Alright, let me get rid of this, and we will begin our new material in earnest. Alright, today we're going to cover chapter and section 3.4, which is entitled Measures of Relative Standing. Alright, what this is going to do is give us ways to compare the proverbial apples and oranges, and do it in a kind of a clinical and scientific manner. Basically, in this section, let me put the objectives for the section first. It's kind of an ambitious section. First topic we're going to talk about is z-scores, then percentiles and quartiles. Percentiles, I think everyone's heard of. Quartiles, maybe some. Beyond that, we call the 5. Oops, get the eraser out. The 5 number summary, leading ultimately to the box plots, otherwise known as box and whisker diagrams. Alright, so those are the main objectives for today's lecture, and let's talk about z-scores first. Well, the book's formal definition of a z-score is this: is the number of standard deviations a value is above, or of course below, eraser time, or below the mean. So what this does, it gives us a way to measure relative position for any data value in any data set based on the relative standing above or below the mean. The formula for z-score is very simple, and I'm sure some of us have seen this before. Z equals, well, let's say you're interested in the z-score of a particular x value. All you have to do is subtract the mean and divide by the standard deviation. Now notice this implies a sample scenario where you're subtracting a sample mean and dividing by a sample standard deviation. Or if you're working for a population, you subtract the analogous population mean and divide by the population standard deviation. Alright? Let me change something here, and I'll give you an example. I'm going to resize the canvas. Give me a minute here. Put it on pause. Alright, we're back. Let's see. Let me, as an example, pose you a question. Which is better? And let me give you a couple of scenarios here. On the SAT test, you get a score of, let's say, 1840. Or on the ACT college entrance exam, another type of college entrance exam, you get a score of 26.0. Which of these is better? Well, if we had more information, we can convert and get things in terms of z-score, which is really your relative position to the mean. Let's say the SAT scores, we'll talk about a population here, has a population mean of 1518 and a population standard deviation of 325. Let's say the ACT test has a population mean of 21.1 and a population standard deviation of 4.8. Which of these scores is better than? Which one would you guess? Well, it's kind of hard to tell. Well, the idea, we can be very scientific about this if we convert to z-scores. Alright, I'll take my SAT score of 1840, and again I'll subtract the mean and divide by the standard deviation. Well, we punch this out on the calculator very quickly, and I get a z-score of 0.99. That tells me I'm 0.99 standard deviations above the mean. Please note, if your score, your raw score, is above the mean, your z-score will of course be positive. If your z-score is below the mean, if your raw score is below the mean, your z-score of course will be negative. How about the ACT situation here? Well, we've got a score of 21.1. A score of 26.0. Easy mistake to make. So be aware of that. If it can happen to me, it can happen to you. So a raw score of 26.0 and a mean of 21.1, and I'll divide that by a standard deviation of 4.8. I grind that out and I get a z-score of 1.02. And what that means is an ACT score of 26 is a total of 1.02 standard deviations above the mean. So we can see that this is a slightly better z-score. So which is better? Well, the higher z-score is better. Not the one that's farther away from zero necessarily, but just the one that's higher. The ACT score is better because its z-score is higher. Alright, so let me write that down. A score of 26 on ACT is better because it's a higher z-score. Greater z-score. This z-score is greater than this z-score. Not by much, but certainly is greater, right? Alright, let me highlight what I said earlier. If you look at your z-score formula, it is entirely possible that your raw score would be below the mean, and if this x value is less than x bar value, of course your numerator will be negative. So if your z-score is below the mean, hang on a minute. If your raw score is below the mean, that implies your z-score will be negative. Your numerator will be negative, and of course your standard deviation is always positive. Similarly, if your raw score is above the mean, that means your z-score will always be positive. Right? And there are some homework examples I'm going to assign to you that will contain examples of both. Okay? Alright. Recall. A little more room here. Recall from section 3.2, we gave boundaries of what I call usualness if you have a data value that is within 2 standard deviations of the mean. In other words, falls between x bar plus 2s and x bar minus 2n. If you're within those criteria, we call those values usual, and anything beyond that, high or low, we somewhat arbitrarily label as unusual. You may recall we talked about that last time and had a couple of homework problems that discussed that idea. In section 3.4, it's analogous because your z-score is your number of standard deviations you are above or below the mean. In terms of z-score, this value here, x bar plus 2s, is 2 standard deviations above the mean, thus has a z-score of 2. This value, x bar minus 2s, is 2 standard deviations below the mean, thus has a z-score of negative 2. Thus, if your z-score of your particular value is between minus 2 and 2, we call those usual values. And again, somewhat, it may seem somewhat arbitrary, but it really isn't. Any z-score above 2 we will call unusual, and any z-score below minus 2 is, of course, we deem unusual. Okay? So bear that, and there are some homework problems in that regard. Fresh sheet of paper here. Alright, let's pick it up again. Next topic I want to talk about today is percentiles. Hang on a minute. Alright, the next thing we want to talk about here is percentiles. Alright, it turns out there are 99 percentiles which separate partition data into 100 groups, each containing 1% of your data values. Well, in the long and short of it, let's say I take a test and I am scoring in the, say I'm in the 70th percentile. This is our shorthand for the 70th percentile. This score really separates the bottom 70% of data from the top 30%. So, like if I scored in the 70th percentile on an exam, that means I have done better than 70% of the people and worse than 30%, the top 30%, right? All right. There is a formula to convert there is a formula, pretty easy formula, in order to compute the percentile value of a given data value. To convert, to find a data value to percentile. Pretty easy formula. Let me give it to you. This is the word convert data value to percentile. It's according to this very simple formula. The percentile of a given data value x equals the number of data values less than x divided by the total number of values, or very simply the sample size, times 100. Right? Well, to get this numerator, you've got to sort your data first, and what I want to do is cite an example in the book. Please pause and get your books out and turn to page 116, and we're going to look at example 2 in the book on page 116. Alright, there you will see a bunch of data specifying movie budget values of 35 selected films ranging from 4.5 million way up to 225 million or so. Alright, so what I'm going to do is, looking at this example from the movie data, find the percentile value of 29 million. You'll see there is a value there in the list that specifies 29 million in the movie budget. Alright, so very simply, the percentile value of 29 million is the number of movie budgets less than 29 million. That means strictly less than. If you look at the formula up here, alright, it's a strict inequality. So it's all those values on that list less than 29 million, and there's 6 of them. Thankfully, this data set is already sorted for us. There's 35 total values. So I take that fraction and multiply it by 100 to turn it into a percentage. I get about 17.14 and change, and we round it to the nearest integer when computing percentiles, as stated in the book. Alright, what we have just computed is the percentile value of 29 million, and we summarize that in this fashion. We then claim the 17th percentile of this data set is 29, or remembering the units here, these numbers all refer to millions of dollars. All right? So the 17th percentile is 29 in millions. All right? All right, again, I can interpret this we'll say a movie budget of 29 million separates the bottom what? The bottom 17% of all movies from the top 83% of all movie budgets, of course, in millions of dollars. Okay? So, a pretty easy way to convert raw values to percentiles according to that formula. Okay? Let me get a new screen here. Alright, seems to be going pretty well. Settle down a little bit. Let me get to the top of the screen, and we'll carry on. Alright. We're going to talk about some notation. All right, now we want to work it in reverse. We computed percentile from data values. Now I'm going to want to go the other way. I'm going to, given a percentile, convert it to a data value. All right, so we're going to need some notation. The formula for this is a little more complicated. So let me get some notation for. be building up a new formula. Notation. Little n. Oops, get the eraser out. N, of course, is going to equal your sample. I bet we all knew that. Alright, let me write that again. Little n refers to our sample size. Little k is going to be the given percentile capital k. And this formula is going to tell us where to look in our sorted list for the percentile value of interest, and P sub k, as we already know from our last example, is the kth percentile, where k is a number between 0 and 100. Okay. Alright, what we're going to do here is convert a percentile, a given percentile, to the reverse of the previous. Alright. Again, we're going to work with this movie data. From the movie data, given in example 2, on page 116, we want to find the 90th percentile. Again, this is our notation for the 90th percentile. All right? 90th percentile. Okay? Alright, there is a formula. It doesn't give us the 90th percentile directly, but it does tell us where to look. L is going to be our locator function. And it's a pretty simple formula. Basically, you take your percentile you're looking for, divide it by 100, multiply it by your sample size. Right? This tells us where to locate the kth percentile in the sorted list. Okay. Alright, let me give you an example for this. In our movie data, the percentile of interest is your 90th. Alright, so to find the 90th percentile there, I plug in k equals 90 over 100 times, well, your n value is 35. That movie data has 35 elements. Alright, we grind this out with our calculator, and I get 31.5. Alright, so there is different rules on what to do with L depending on whether it's a whole number or not. Let me go through this kind of simply this first time through. If L is not whole, as it is here, not whole, 31.5 is certainly not a whole number, we must round it up to the nearest integer. So I'm going to say here is L is then, according to this rule, if L is not whole, round up. I'm going to call L 32. Alright? This tells us the 90th percentile is the 32nd value from the bottom of your sorted data list. Right? So if I look at that data on page 116 and I start at the bottom at 4.5 and count up 32, it turns out 150 is that 30-second value. So then I claim the 90th percentile of this data list is 150, or of course in the units, realizing that each of these is in millions of dollars, $150 million. Okay? Let me give us another example. Same data. Another example from the movie data. I'm going to say find the 60th percentile. All right. Well, again, you can't get it directly, but the locator function does tell you where to look. So I take my 60th percentile, so my k value is 60, divide by 100, and multiply by the number of data values. And if I punch that out on my calculator, I get 21. Now remember, this is a whole number, and the rule changes a little bit if L is a whole number. So in the last example, L was not whole. Let me briefly say here, if L is whole, P sub 60 is the mean of the 21st value on the list and the next one up. Kind of simple language here, but I think you get the idea. In other words, the 60th percentile is the mean of the 21st and the 22nd value in your sorted data list. Right? Alright, so if I look on the raw data sheet, I claim, well, the 21st value, it looks like it's 70. And the 22nd value is 72. So I take the mean of the 21st and 22nd value, and of course that's 71. Or of course we know that we are in millions of dollars here. So P sub 60 is 71. The 60th percentile in this data is 71. Or of course in millions, $71 million. Okay? Alright. I'm going to ask us to pause again. Pause here and look at the flow chart on page 118. Pause now, please. Basically on that flow chart on page 118, you'll see the crux of what to do, how to find your value, is in this decision diamond that asks you, is L whole? Right? And of course the book is much fancier than I can replicate here by hand. And the answer is, if the answer to this question is no, right? If L is not whole, then we round L up to locate the needed percentile. Okay? And if L is whole, if the answer to that question is yes, the percentile you seek is then the mean of the Lth value and the next one up. Of course, in the sorted list, right? All right. All right, so we know how to find percentiles now given data values and vice versa. What I want to talk about now is quartiles. Now the formal definition of quartiles is this, right? There are 3 quartiles. Namely, Q1 and Q2 and Q3. And as you might predict, these three quartiles separate or partition the data into fourths, each containing 25% of the data. Yeah? Now, clearly, we should be able to recognize that the first quartile is equivalent to the 25th percentile. And we know from the previous examples that we can find the 25th percentile, right? Similarly, let me get my eraser out here. That's a Q there. Q sub 2. Similarly, the second quartile is equivalent to the 50th percentile. And that's also equal to the median. Remember, the median is the midway point that separates half the data below from half the data above. And similarly, the third quartile is the 75th percentile. Alright, so because we know how to compute percentiles already, well, we know how to find quartiles also, because quartiles are really percentiles. I want to look at example 6 in the book on page 120. Basically, we're going to be working from the movie data. Again, good as data block as any. I'm going to say find Q sub 1. Find the first quartile. Well, we know that's the 25th percentile. And we know how to find the 25th percentile. You take your percentile of interest. You divide by 100. You multiply it by the number of data values. That will tell you where to look in the sorted data list for the 25th percentile. That turns into 8.75. And notice here, L is not whole. So we round up to the nearest integer. So I'm going to say L is then 9. And that means the first quartile is going to be the 9th one up from the bottom on the sorted list of that movie budget data. Alright, so P sub 25, which equals the first quartile, is the 9th on the list, and if I look at my raw data, it looks like 35 million is the 9th up from the list. So let me write that down. Q sub 1 is 35, or in millions of dollars, $35 million. All right? Now, let's see if we can find this out for the other two quartiles, Q2 and Q3. Let me briefly grind that out here. So, now, let's find Q2 and Q3 in similar type fashion. Alright, Q sub 2 is the 50th percentile. So you take your percentile of interest, divide by 100, multiply it by 35, and I get 17.5, which then I will round up to 18. So the 18th value on the list, 18th from the bottom. And I believe that's 68 in millions of dollars. So Q sub 2 equals 68. And one more quartile to find. Q sub 3 equals, well, we know that's the 75th percentile. That's going to be 75 100ths of the way up on the 35 deep list. If I punch this out, I get 26.25. And again, if L is not whole, you round up to the 27th value, right? And that's where you want to look for Q3. So Q sub 3 is going to be on the list. I believe the 27th up from the bottom is 113 and 113 million. So when I ask you for the 3 quartiles, you will respond Q1 equals 35. Get some more room here. Q2 equals 68 in million, and Q3 is 113 in millions. Okay, so we can find now quartiles now as well. Okay? Alright. Hello? Alright, back now. Very good. Alright, one more topic, really 2 more topics I want to talk about. Really 1.5 maybe. Next thing I want to talk about is the 5-number summary. Now, don't panic. Really, we already know how to compute the 5-number summary. All the 5-number summary is the 3 quartiles, Q1, Q2, Q3, which we can easily calculate as percentiles, along with the min and max value tacked on top and bottom. Right? So we've already computed a 5-number summary, haven't we? Well, essentially. So for the movie data, the 5-number summary is, well, if you look on the the minimum value on the list, it's 4.5 in millions. The first quartile was 35 million. The second quartile was 68 million. The third quartile was 113 million. And the fourth quartile was 225 million. Alright, probably should label these min, Q1, Q2, Q3, and the max value here, and this is my 5-number summary. Now, again, all you need for 5-number summary is the quartiles, which is a relatively easy calculation, along with the min and max values, which you typically get by inspection. Okay? Once you've got the 5-number summary, it's a very easy proposition to sketch what we call a box plot. All right? Box plot is also known as box and whisker diagrams, which you'll see why in a minute. All it is, it's a graphical representation of the 5-number summary. What I'm going to do here is I'm going to plot these values approximately on a hand-drawn linear scale. What I'm going to do is plot the min value. The min value is 4.5, and I'll label it here the min. The max value is 225, and I'll put it somewhere up here, and I'll call that 225 and the max. Now I'm going to want to plot these at least approximately relatively within these boundaries, 4.5 and 225. Plot the quartiles therein. This is how I do it. I find this is a nice, neat, easy way to do it. 68. Let's say I want to plot 68 somewhere on this scale between 4.5 and 225. Let me ask you, is 68 closer to 4.5 or is it closer to 225? Clearly 68 is closer to 4.5, so I'll eyeball it down here somewhere and I'll label it as 68, and that's what I call the second quartile, or the median value. Alright, now I can go after Q1 and Q3 here. Let's look at Q1, 35. Is 35 closer to 4.5 or closer to 68? Well, it's kind of hard to tell. I think it's right about in the middle. Right? Not always so, but in this case, I'll put Q1 about halfway between minimum and Q2. Similarly, 113, the third quartile. Right? That is, let's see, 113, is that going to be closer to 68 or closer to 225? I think you'll agree with me. It's much rather closer to 68. So I'll plot the third quartile there. All right? And what I have done, I have got the framework for the box and whisker diagram of this data. All I do now, and a picture tells 1,000 words, create a box there, and that is the box plot or the box and whisker diagram for the above data. All right, of course I could have done this a little more clearly, but again, we can look in our book. Our book does a much better job of drawing this box plot than I can by hand here. A box plot gives us a nice summary of the data. Notice 25% of your data is going to be in this range. 25% is going to be in this range. 25% is going to be in this range. And 25% of your data is going to be spanned out in this final range here. So it gives a good idea of the spread of the data, gives a good obvious view of where the center of the data is, and tells a lot about the data at first glance, really with one glance. Really, box plots are good for comparing two sets of data, and you can do it very quickly and tell a lot about the two sets just by looking at box plots of the two data. As we'll see, it can be generated, or they can be generated very easily with the TI-83 and 84 calculators. All right. To figure out how to do this, I'm going to ask you to see the using technology gray box in our text on page, you see what page it's on, page 125. It gives user-friendly instructions on how to generate these box plots, and also I have posted a YouTube video on constructing box plots, and I have located that posted in our online class 2 folder. Okay. All right, so that's more or less the end of the lecture today. So also please see review. I'm sorry, not review. Reading assignments. And homework exercises. A file again posted in the online class 2 folder. And of course, don't forget the online exam 2. All right, and I'll send out details in that regard via email. So this closes the video file, the video lecture for online class 2. So go ahead and view the rest of the materials in online class 2 folder, and of course prepare for the online 2 exam. That is all.